In this video, we're going to look at how the equilibrium constant K changes when changes are made to a reaction. Throughout this video, we want to keep in mind the fact that K is equal to the concentration, or it could be the pressure of products, divided by the concentration of reactants. So products are always in the numerator. And we also want to keep in mind that the exponents come from coefficients. So that will help us understand how to make changes. So in the first example, we are given a balanced chemical equation, and we're given the equilibrium constant for that balanced chemical equation. And we're asked, okay, if the K for this original equation is 2.2 times 10 to the 6, what would the K be for this related reaction that comes after? And so I have to figure out how those two reactions are related. So I'm looking for where things are in common. So I notice COF2 is here and COF2 is there. So it becomes a product. I notice that CO2 is a product here, but a reactant here. And I notice CF4 is a product where it's a reactant in the second one. So it looks like one change that's made is that we flip-flop the reactants and the products. They got switched around. I also look at the coefficients, and I notice that the coefficients are 2, 1, and 1 in the original reaction, and they're 4, 2, and 2 in the reverse reaction. So we see two changes being made. First, the reactants and products get flipped around, and second, all the coefficients get doubled. So I have to think about how those two changes would manifest themselves in the K expression. First, because reactants and products are flip-flopped, that means that we would have to flip the numerator and the denominator order. So switching reactants and products means that the final K is going to be the reciprocal of the original K. And then the second change that was made is doubling all the coefficients. And since coefficients are exponents, if we make all the coefficients 2 times as big, we're going to have to make the exponents squared. So we'll take the 1 over K that's already been adjusted for the fact that we switch reactants and products, and we're going to square that. So to figure out an actual value of K for this reaction, you're going to do 1 divided by 2.2 times 10 to the 6th, and we will square that. And when you do that, you get 2.1 times 10 to the negative 13. We're going to look at one more example, and we're going to keep in mind those same principles. Like if you flip the reactants and products, you take the reciprocal of the K value because you're switching the numerator and denominator of your K expression. And if you change the coefficients in some way, that affects the exponent that you take to the K value. So in this one, we're given a reaction that we are trying to get to. This first one is our target. We don't know the K value for that. We are given K values for 2 other related reactions. So again, kind of like before, I'm going to look for what things do we have in common here. So I noticed that CO2 is a reactant here, and my target is a product. They have the same coefficient. I notice that H2 is a reactant here, and it is a product here, but it's also a reactant here. I notice CH3OH is a product, and it's a product there. And water, I notice, is a product in the original, but a reactant here. So I'm looking at my 2 possibilities, my 2 reactions that I need to adjust to get to the target reaction. It looks like in this first reaction, things that are in common, CO2 and H2, we need to flip them around. Like we need to take this reaction and reverse it. So we need to flip products and reactants. And that would cause K to be its reciprocal. And it looks like the coefficients, at least for most of it, the coefficient on the CO2s match, the coefficients on the H2Os match, and I'm not going to worry about the H2 yet because I notice it's in a couple places. So I think if I figure out other things, that will kind of fall into place. If I look at my second reaction and I compare that to the original, I notice I've got this as a product here and this as a product there. So it doesn't look like I need to flip anything. I notice I've got hydrogen that's a reactant and it matches the hydrogen that's a reactant here. So I'm not going to make any changes to the second reaction. I'm going to keep that the same. So I'm going to change how I write that first of the two reactions I know about by flipping it around. So I'll make this H2 plus CO2 is in equilibrium with CO and H2O. And I'm going to try to add together these two reactions that I now have hopefully adjusted to match. So like I'm not looking at this anymore, I'm looking at how I've rewritten it. So adding together all my reactants, it looks like I have one CO, I've got three H2s, and I've got a CO2 here. So CO plus three H2s plus a CO2. And my products, I have CH3OH, I've got CO, and I've got H2O. And I notice there's a CO on both the reactant and product side of my added together reaction, so I can cancel that out. And then it looks like I have successfully matched this to my target reaction. So I've made one change, I've flipped over the K2 and I've kept the K3 the same. Now I need to think about how am I going to combine these two Ks. When you add multiple steps of a reaction, you're going to end up multiplying their Ks. And so since we had to flip over K2, what we're going to do here is take 1 over K2 multiplied by K3, which has no changes to it because no changes are made to that second step. So that means K1 is going to be equal to K3 divided by K2. And if we wanted to get a number for that, you take 1.4 times 10 to the 7th divided by 1.0 times 10 to the 5th, which would give me 140. If we're talking about a multiple choice section or a multiple choice question, it would be likely to stop at some kind of expression like K3 divided by K2, which would not require you to put anything into your calculator. If it's more of a free response type of question, then it might expect you to be able to report the numerical answer. So that is how you adjust K based on changes to the reaction. Either take its reciprocal by, if you flip the products and reactants, you change the exponent if the coefficients are changed by a certain factor. And if you're adding together several reaction steps, you will multiply their K values for each individual step.